Today we have the pleasure of having Dirk Erhard from Universidade Federal da Bahia, and he's going to tell us about weak coupling limits of the anisotropic KPZ equation. Thank you, Dirk.
So yeah, thanks for the invitation. So, quite honored to speak here. So the work I will talk about is actually a series of works with my co-authors Giuseppe Cannizzaro, who is now at Warwick University, Philip Schönbauer, who was a PhD student at Warwick, but now left academia, and Fabio Giulianelli from Vienna. And okay, so the talk at the end of the day will be about the KPZ equation, and some of you saw it probably already. But so let me start with some kind of motivation why it's worth it to look at it at least. So let me start to talk about Gaussian versus non-Gaussian behavior. So probably the first big result, maybe next to the law of large numbers one sees in the first course of probability theory, is the classical Clt, which essentially says that if you look at a random walk and you look at the last point of the random walk and you scale it properly, then this converges to some Gaussian random variable. Yeah? So then the next big result one sees is stochastic theory, which says, well, instead of looking only at the last point of the random walk, okay. I can also try this. So sometimes this works better. Okay, can you hear me better now?
Yeah, no, I think it's fine. It's something small, but because there is one participant which is unmuted, maybe I thought it could get better. But you okay. You don't need to worry about.
Okay, I just stopped hearing it. But okay, so then I will continue. So then, well, there's stochastic theory, right, which essentially says if you look at the whole trajectory of the random walk, you rescale properly, then again the limit is Gaussian. So you see in the Clt, you look really at the kind of the evolution of one point. In Donska, evolution of a trajectory that depends on time. And then a natural question is, what is if you have something that does not only depend on time, but also on space? Yeah. So there, of course, you have much more flexibility of defining what you want to look at. And so just to give an example, one example is what we call the symmetric exclusion process. Again, many of you saw it, maybe some of you did see it yet, so let me shortly talk about it, which is actually really just an example. So what is the exclusion process? Well, so imagine on the d-dimensional lattice, you look at a bunch of random walks that are essentially moving independently of each other, but respect the exclusion rule, meaning that two random walks are never allowed to be the same site at the same time. Yeah, so really, the thing how it works, let's say in dimension one, let's say with nearest neighbor interaction is that there's some spots on the line where there's no particle. At some spots, maybe there will be particles. Yeah. Maybe there's a particle here, there's no particle here. Maybe something like this. And the way it works that each particle wants to perform a simple random walk. So if you look, for instance, at this guy, let's say it does a nearest neighbor random walk, so then it has two exponential clocks, one pointing to the left, one pointing to the right, and waits until one of these two clock rings. Let's say the one to the right rings first, so it would like to jump on top of the other, but this is forbidden by the dynamics. Yeah. However, for instance, this guy here, it has two exponential clocks, one pointing this direction, one in this direction. Once one of these two clocks rings, you will simply do the jump. Yeah? So in the exclusion process, random walks are indeed independent unless they're at distance one or whatever is the range of the transition current. Yeah? So this would be one example of a process that depends on space and time. And so one thing that we know about it that has an invariant measure, mu, let's say, which is the product Bernoulli, let's say x and zd, yeah, which is the product Bernoulli with some fixed parameter rho. So the parameter needs to be the same for all sides. Okay, so now you have space-time field, and then you can ask again, well, is there, if I rescale this process in a sensible way, what kind of limit will I obtain? Will I again obtain a Gaussian limit? And the answer is essentially yes. So this result says that if the transition currents of the underlying random walks are symmetric, and under some moment conditions, And if you start under the invariant measure with mean rho, then for every smooth, compactly supported function f, the function y, t, and f, which I will explain now, converges to a Gaussian process. So let's look at this y, t, and f, what is happening here. So again, some of you probably saw this already, but not everybody. So what we do here is, well, we sum over all points in ZD, x and ZD, and then we look at f of x divided by n. So now what is happening? F is a compactly supported function, say support has size 1. Yeah? So f of x divided by n will be 0 unless x divided by n is of order smaller than 1. Yeah? So actually, in the sum, the number of points is really of the order n to the d. Yeah? Okay, so you do this, and then you multiply by this funny factor here. So what is happening here? You look at the exclusion process at times t times n squared, so you rescale time, yeah? And you do an additional recentering. That's what we know from this classical center limit theorem, right? And so all of this you divide by n to the d half over 2. And so again, this is really classical center limit theory because, as I said, since f has a compact support, the number of points in the sum is of the order n to the d. So we divide by the square root of the number of points in the sum. And so it turns out that this is a process yn converges to something called Ornstein-Uhlenbeck process, which is again Gaussian. Yeah? So you see we have this kind of three levels, looking at kind of the evolution of one point, evolution of a whole trajectory depending on time, and the evolution of a field that depends on space-time. The limit is always Gaussian. So now it's kind of natural to ask, so since Gaussian always pops up, so no matter what you do. But still, so now it's still natural to ask how stable is this Gaussian universality class? So meaning I take my model, which I know converges to something Gaussian, and now I do a small perturbation. If this Gaussian universality class were stable, then the small perturbation really shouldn't change much. Yeah? And in the framework of the exclusion process, this has been done, this has been studied actually, for the one-dimensional case. Yeah? So now let's change the game a little bit in the one-dimensional exclusion process. So the transition kernels are still essentially symmetric, but there's some kind of a slight bias to the left or to the right, let's say to the right. So we assume that the kernel has an asymmetry of order 1 over square root of n. So what do I mean with asymmetry of order 1 over square root of n? Well, so if you look at one of these exclusion walkers, yeah, let's say the nearest neighbor case, so it has an exponential clock pointing to the left and one pointing to the right. Yeah? And so in the symmetric case, both of these clocks would have the same rate, say rate 1. What's happening now that I say, well, maybe the one to the left has rate 1, and the one to the right has rate 1 plus a little bit, 1 over square root of n. So it's really a small perturbation. As n goes to infinity, this perturbation, or this 1 over square root of n actually vanishes. So it's kind of very reasonable to expect that the limit really shouldn't change much.
I have a question, Dirk.
Yes.
Is it really square root of n here, or is it square root of n squared? Because your time scale is n squared. And okay, it seems that at the level of one particle, yes, the competition between the drift and the central limit theorem occurs when, okay, well, if you take the square root of your time scale. So, but maybe I'm mistaken there. But,
no, I think you take this and then you rescale time. Yeah.
So yeah. Do you consider here really 1 over square root of n or 1 over n?
Square root of n.
Okay.
Okay. So and what is actually happening? So if you then calculate the limit, so it turns out that the limit is not Gaussian anymore. And this is not something that is because of the specific definition of the exclusion process, but the same phenomena can be observed for other models. Yeah. And it turns out that the limit one obtains is the limit, but not the Gaussian. What do you mean? I modify the limit, but not the Gaussianity.
Maybe you can unmute yourself, Milton.
Yeah, I'm just answering your question, Hubert. So if you do as you wanted to do, then you modify the limit, but it's still Gaussian.
If you take 1 over n as a perturbation, you mean?
Yeah, yeah.
Okay. This is what you mean. Okay, now I understand. Okay. But so here in this case, it's 1 over square root of n, you change the limit, and the limit is dramatically not Gaussian anymore. And so actually what will really happen is that if you look at this scale, 1 over square root of n, then you add some kind of a nonlinearity to it. So as Gaussian object, you can kind of imagine a linear objects, but this 1 over square root of n adds really a nonlinearity to it. And so it turns out that this limit can be described in terms of what is called nowadays the KPZ equation, which will be the main object of this talk. And so, well, some of you saw this equation, but still now I will try to introduce it a little bit. So you see, if you look at this equation, so the unknown is h, we search a function h, which depends on space and time. And this equation says that, well, the left-hand side of the time derivative, so the change of this function when you add a little time increment, is given by the sum of 3 terms. So the first term here is some constant mu times the Laplacian of h. This term is what we call the nonlinearity. I will still talk about this. And this term is square root of d times the noise. And so this noise, the psi here, is what is called the space-time white noise. Okay, so let's okay. So what is space-time white noise? So space-time white noise is a Gaussian process that depends on space and time, and its name is space-time. So once you have something Gaussian, the only thing you need to do to characterize it, to say what does it mean and what's the covariance structure. So it's centered, so the mean is 0. And the covariance structure is often written in this way. So the expectation of psi of t x times psi of s y is Dirac delta in time times Dirac delta in space. So if you have never seen this before, maybe one way to picture this is that, well, you look at space-time, Tx, and now to each point of space-time, you associate an independent Gaussian random variable. So how will this field look like? So I mean, first of all, from stochastic point of view, it's nice, right? I mean, because everything is independent, everything is Gaussian, so we are essentially able to do explicit computations. From an analytical point of view, if you ask yourself now, okay, so boundary motion is essentially 1/2 Hölder, so what about this case? It's actually not very nice. It's actually terrible. So there's very poor continuity properties. And to see why, so well, essentially, so imagine you take a very small box in space-time, a very small box. How many points are in a small box in space-time? Well, still uncountably many. Now, to each of these uncountably many points, you associate a Gaussian random variable. And when a Gaussian random variable can be very large, okay, probability is maybe not large, but it can be very large, it can be also very, very negative. Since in a small box with uncountably many points, essentially each crazily large value and each crazily small value you will observe is really highly oscillating. And so it's not smooth at all. Okay. So this is the noise term. So then the Laplacian, so once you've known the Laplacian the equation, it usually has a tendency to make the solution look a bit more smooth. So again, if you're not used to this, if you've never seen this before, one way to mention why this could be the case as well. Once you put the Laplacian to the equation, you kind of want the solution to be twice differentiable in space. So you need to have some smoothness property. Okay. And so then there's the last term, this kind of term in the middle. So here the lambda is just some non-negative constant, and the Q is a d by d matrix. Okay. So what is happening here? So you see we have the gradient h, comma, q gradient h. So this term is really quadratic in the derivatives of h, in the first derivatives of h. And how can you picture this? Well, maybe you remember that the gradient of a function always shows into the direction of the vector that shows into the direction of the strongest, of the largest increase. So the gradient of a function really is something that depends on the slope of the function at that point. Yeah? So this really means that this term in the middle, this nonlinearity, is something that depends on the slope of the function h. Yeah? And the matrix Q essentially more or less how you want the slope dependency come into the game. Yeah? So there you have kind of quite some freedom. In dimension 1, Q would of course be only a number, and then you can absorb it simply the constant lambda. If D is not 1, then it's a real matrix. Okay, so that's the solution. That's the point about the equation. So now you see we have essentially 4 parameters to play with: nu, lambda, Q, and D. So nu regulates the strong of the smoothing, D is the strong of the strength of the noise, and lambda and Q modulate the nonlinearity. And so what we will do in the following, we will not play with mu and with D, we set them to 1/2 and 1 respectively. And so in the seq we will play rather with lambda and with Q. Okay. Okay, so the first thing when you have an equation, well, is you try to solve it, or at least to show that it has a solution, maybe a unique solution. However, what turns out is that since this object psi here, as I said, has very poor continuity properties, it's highly oscillating. In order to show well-postedness, that's really bad news. Yeah? And it turns out that actually there's no clear way of showing well-postedness of this equation. And so one way maybe to picture this is the following. So if you look at the equation without the nonlinearity, this equation we can solve. You can actually explicitly write down the solution. And then you can ask yourself, well, if the nonlinearity were not there, what kind of properties does my function have? So how smooth is it? And this is something we can really compute. Yeah? And then the idea is the nonlinear equation shouldn't be smoother than the linear equation. And it turns out that the best regularity you can hope for is minus d over 2 plus 1. And actually there's a minus here. So in particular, in dimension 1, you see this would be 1/2 minus. So this means it's almost 1/2 further, it's Brownian motion. In dimension 2, it would be a little bit less than 0. In dimension 3 and high, it would be a negative regularity. So just a word about this. So once the regularity is negative, then actually we don't think about h as a function, but as a Schwarz distribution. Yeah? Okay, and you can really make sense out of it that for negative values that this is really, well. So for instance, dimension 3, the regularity would be minus 1/2. This essentially means that h is the derivative of a 1/2 Hölder function. Generalized derivative. Okay. Anyway, if you now take the gradient of h, you lose 1 in regularity. So gradient of h has regularity minus d over 2. That's something negative. And now essentially what you want to do is you want to square it. And there's now an old result that says that if you have something of negative regularity, then there's no canonical way of squaring it. Yeah, so it's really a result to say that's not possible. And well, that's maybe a bit strange, but if you have never seen it before, one way to picture is the following. So instead of looking maybe at this equation, we can look at some smooth version of the equation. And then take out the smoothing and then hope that it converges. It, however, then turns out that this nonlinearity would simply explode. This is essentially what we mean that this nonlinearity is not well defined. So there's no way of approximating the nonlinearity with smooth terms. It simply does not converge. Okay. So that's kind of the problem. However, in dimension 1, one still kind of knows how to make sense out of it. So this was a very active area in the last years. And by now there are many, many approaches, and all of them use some kind of renormalization, meaning that you look at a smooth version of the equation, you look at the limit as you take away the smoothing, and it turns out that there's a divergence, but we know how to cure it by plugging in some renormalization constants. And by now there are several approaches. The first is maybe the Kohl-Hopf transform. And what is the Kohl-Hopf transform? Well, for this particular equation, dimension 1, we know that the exponential of h satisfies an equation that's much easier to handle. And then we can solve this equation, then we can go. You can formulate in terms of a martingale problem. So Milton knows much more about this because he was one of the people developing it. And then there's some pathwise approaches like regularity structures, path distributions, and rough paths. Yeah? So in dimension 1, at least the problem of well closeness is essentially solved. The problem with these is that directly at least these simply break down if dimensions 2 are high. Yeah. And this makes, of course, the equations a bit more interesting to study. Okay, so I mean, what can you do then? So whenever you want to study the equation, you look at some kind of a smooth version of the equation. And well, then still you try to study properties of this sequence of equations once you take away the smooth. And what could you be interested in, or what are we interested in, is the large space-time behavior. Yeah. So if you really look at large space and time points at the same time. And one interesting feature is to know the relevance of the nonlinearity. So people working in polymers probably heard about this already. And with this, I mean the following. So picture the equation where lambda is 0. So the nonlinearity is not there. Yeah? So then you can study this equation. And then you want to compare it with the equation where lambda is not 0. And you would like to know if maybe on large space-time scales, these two equations, the one without nonlinearity, the one with nonlinearity, maybe have the same features. If this would be the case, you would say that nonlinearity actually is not relevant. It can, of course, also happen that the nonlinearity changes completely the behavior of the equation. Then we will say that the nonlinearity is relevant. And this is one thing we would like to understand. So what could you do now? I mean, now you try to have a kind of a first guess in order to know what you want to prove, actually. And so one thing you can do is you can look at scalings. You can try to check how this equation behaves on the scalings. And one way to do this is you first take your linear equation. You check, is there maybe some rescaling of space and time that leaves this linear equation scale invariant? And then you take the same scaling for the nonlinear equation, then you check what happens. So let's do this. So it turns out if you take this scaling, so what do we do here? We divide time by epsilon squared. We divide x by epsilon. So you see, as epsilon goes to 0, t divided by epsilon squared goes to infinity, and x divided by epsilon also goes to infinity. So we really look at large space time. Yeah? And it turns out that what you additionally need to do, you need to multiply it with this factor here. Epsilon to the 1 means d over 2. If you do this for the linear equation for the one where lambda is 0, then in law you change nothing. So in particular, you see that in dimension 1, you need to multiply by square root of epsilon. Dimension 2, you don't need to do anything. In dimension 3 high, you can divide by epsilon. If you now take this scaling for the nonlinear equation, you obtain the following equation, at least in law. So what you see is that this Laplacian here is untouched. There's nothing really happened. The noise is untouched. Yeah? And this is actually not surprising because we took this scaling that leaves the linear equation invariant. The only thing that we observe is that in front of the nonlinearity, there's an additional factor. And if this factor explodes or goes to 0, of course, depends on the exponent, d minus 2 over 2. So let's work this exponent out. So d minus 2 over 2. So if d is equal to 1, this would be minus 1/2, I think. D is equal to 1, that's minus 1/2. That's correct. If d is equal to 2, it would be actually 0. Yeah? And it turns out to be positive if d is 3 or larger. Okay. So what does this mean? So this means that this epsilon to the d minus 2 over 2 diverges in dimension 1 and goes to 0 in dimension 3, and in dimension 2 nothing happens. Yeah? So this kind of suggests that when you take epsilon to 0, yeah, so this means you really zoom out in space and time. As epsilon goes to 0, that in dimension 1, since the nonlinearity formally explodes, is that the nonlinearity should formally be the dominant term. In dimension 3 and higher, however, this prefactor goes to 0, as epsilon goes to 0. So this means that on large scales, kind of the nonlinearity loses its relevance. Yeah? And it turns out that dimension 2 is kind of the critical case. Yeah? So it really suggests this. Okay. Of course, that's only a formal argument, so that's not a proof. But at least in dimension 1 and 3 and higher, it completely suggests the correct things. So in dimension 1, for instance, we know by now that the nonlinearity is indeed relevant. And we actually, by now we know the correct scaling that you need to take. And in the limit, you see something called the KPZ fixed point, which is not Gaussian. And we also know that in dimension 3 and higher, there are some mathematical results that, so for D at least 3, if you take Q, the identity matrix, yeah, and lambda small, yeah, then it turns out that the nonlinearity really is irrelevant in the sense that you can, looking at this scaling that I wrote down, as epsilon turns to 0, H epsilon converges to the solution of a stochastic heat equation. Yeah. And okay, so this essentially leaves us with dimension 2, which is the marginal dimension, where the scaling actually doesn't say much. Maybe says that this nonlinearity is kind of an intermediate scale or something like that.
I have a question about what you're saying in dimension 3 about this result. So,
yes.
So you were saying that there was a problem to define the solution of the equation in general. So
yes, exactly.
So what does the result mean in that case? Because
I see. So yeah, I've been being very precise here. So what you always do is you start the equation with some kind of a smooth noise, yeah. And then it turns out that once you look at the scaling that I wrote down here, so then you, it turns out that this scaling kind of takes away the smoothing of the noise.
Okay.
Okay. Yeah, so yeah, you're completely right. You need to start with something as in this well defined. So either you smoothen out the nonlinearity or the noise, and then you kind of take it away as epsilon goes to 0.
Okay.
Okay. That was a good question. And so this, again, leaves us with this dimension 2 where this doesn't say much. So there has been a conjecture by a physicist who says, well, actually in dimension 2, we need to distinguish between 2 regimes, one that he calls the isotropic regime and the other that he calls the anisotropic regime. The isotropic regime for him is the regime where the determinant is positive. And then he conjectures that the nonlinearity should be relevant. And the anisotropic regime is the one where the determinant is non-positive. This should be the regime where the nonlinearity should not matter much. So in particular, you see here that in this regime, it allows determinant to be 0. So one example is, remember this class is the 0 matrix, in which case you don't even have nonlinearity, and then of course the nonlinearity doesn't matter much or at all. Yeah. Okay. And so let me first talk about what is known in the isotropic regime before going to the anisotropic regime. Okay. So in the isotropic regime, the equation really one looks at is essentially the one I wrote down, but psi epsilon here means that I take a smooth approximation of my noise psi. And which is such that as epsilon goes to 0, psi epsilon converges to psi. And so the mathematical results we only have in the specific case where Q is the identity matrix. Yeah? If Q is the identity matrix, so what you can check is that the nonlinearity becomes this one. So it's really the Euclidean norm squared of the gradient. Yeah? So derivative in the first direction squared plus derivative in the second direction squared. Okay. And so this equation is still very hard to analyze. And so what people did is, instead of looking at this equation, they tuned down the factor in front of the nonlinearity. Yeah? So actually, they took a sequence of lambdas that go to 0 with epsilon, and they did it in this way. Yeah? So actually, the equation they looked at is the one with this prefactor. So where you divide lambda by the square root of log of epsilon to the -1. So 1 over epsilon goes to infinity. Yeah, 1 over epsilon goes to infinity. So log of 1 over epsilon also goes to infinity. So you divide really lambda by something that goes to infinity. Yeah? So you kind of you try to weaken the effect of the nonlinearity. And so what has been shown is that if you now center this guy, then this recentered guy converges to some object which they call curly h lambda. But curly h lambda is the solution to a certain equation, which is 1/2 dth lambda is 1/2 Laplacian of h lambda, thus square root of df times psi, where the df is a certain constant. And this result only holds in the regime where lambda is smaller than a certain critical value, which is square root of 2 pi. If you now think of terms of Wolff's conjecture, this may mean that this conjecture is actually not correct, right? Because what Wolff conjectured is that in this isotropic regime, where the determinant of Q is positive, which is the case if you take the identity matrix, the nonlinearity should be relevant. However, what we observe here is with the linear equation again, so this seems to be in contradiction. However, if we look at this constant df right here, what happens is that as this value lambda converges to lambda hat, which is square root of 2 pi, this constant actually explodes. So this means if you look at this equation with this prefactor, where we replace lambda by lambda hat, then kind of expected that the equation I wrote down here simply does not describe the limit anymore. It must be something completely different. And this is in agreement with Wolff, because it should be kind of clear that once you multiply the nonlinearity with something, it goes very fast to 0, of course, yeah, then you lose the effect of the nonlinearity. So what they were able to do is they were able kind of to determine the window from which onward you will feel the effect of the nonlinearity. So even dividing the nonlinearity by something that vanishes, as soon as it doesn't vanish too fast, you should still feel the effect of the nonlinearity. This is what it morally says. Even though, to the best of my knowledge, there's no result at the very lambda equal to lambda hat. But it's very suggestive at least. Okay. So how did they do this? So why did they choose Q equal to the identity? Because then there's kind of an old trick, which is called Kohl-Huff transformation, which means essentially if you take the exponential of this guy, then it turns it into an equation that we understand better. So it's this equation here. In particular, for this equation, we have a representation of the solution. It's called the Feynman-Katz formula. And then you can work with the representation of the solution and try to prove the result. So that's kind of the big advantage. I mean, the analysis is still super hard, but at least there's a starting point. Okay. So it's the isotropic regime where the nonlinearity should matter much. So our interest was in the anisotropic regime. Yeah? So the choice of matrix that we choose is the following one. It's a diagonal matrix with entries 1 and -1 in the diagonal. If you plug this into the form of the nonlinearity, then the nonlinearity becomes the following. So you have d1h squared minus d2h squared. So one of the features of this equation is that there's no Kohl-Huff transform available, or we are not aware of any transformation that takes the equation and maps it to something that we understand better. So this feature kind of goes away. But I mean, we gain something because we explicitly know the invariant measure, which is the Gaussian free field, which is essentially a centered Gaussian process whose correlations are given by the green function of a Brownian motion. So we lose this Kohl-Huff transform, but we gain an invariant measure. That's actually why we chose this matrix in that way. Yeah. Okay. And so as in the isotropic regime, I mean, this equation a priori is not well defined, so you need to smoothen something out. In our case, it turned out to be slightly more convenient to smoothen out the nonlinearity. And now what I wrote down, you don't need to understand complete in detail. Yeah? But essentially what we did, so N1H is a certain operator that smoothens out the nonlinearity. Yeah? And it works basically as follows. You take some pi1, which is sort of the cut off in Fourier space. So it kind of cuts off all the large Fourier modes. If you do this, then actually you get a function that is smooth. Yeah? And well, you don't, it's not so important why the form is as it is. Yeah? So the main message is really the smoothing that we look at is smoothing out the nonlinearity, keeping the noise invariant, which has a big advantage of keeping the inner measure unchanged. Well, when we take out the smoothing. Okay. Okay, so now we can look at this equation and then, well, we want to understand the large space-time behavior. So there are several observables that you could look at. Yeah? You could look at h of t0 minus h of 0, 0, look at the variance of this. So this measures the variance and how the variance evolves in time for a fixed point. Or you do the same for two space points for fixed time. Or you do something that involves a mixture of space and time. And that's what we do. And then we were really inspired by the particle system literature. There's something that is called the bulk diffusion coefficient. So essentially, the bulk diffusion coefficient is something that should measure how correlations spread over time, how the correlations spread over time, and it's something that can distinguish between diffusive and non-diffusive behavior. So how could you define something like this? So imagine, so forget about all this KPZ stuff. Imagine now you have one particle. Yeah? So this particle, you observe it, it moves around, and maybe is at some position which we call xt. If you have this one particle, how could you decide if it behaves diffusively or not? Well, one way of doing this is you can define a function s of tx, which is the transition probability of this guy, probability that this guy time t is at position x. Yeah? And then what you could do is, maybe you divide by t, you take the integral over space of the norm of x squared, x squared s of tx dx. Yeah? If you do this for Brownian motion, for instance, then it would be simply 1. Yeah? For Brownian motion, the result would be 1. Would be simply the variance divided by t of the Brownian motion, which is 1. And Brownian motion is really something that's diffusive, right? It's kind of the classical diffusive process that one can think of. If, however, this object that I wrote down here, let's say goes to infinity as time goes to infinity, this means it's super diffusive. Yeah? And if it goes to 0, it means it's subdiffusive. Yeah? So this is a quantity that you could look at that kind of can tell you if your object that you want to study is diffusive or not. And so in our case, we would like to do something similar. We would like to define something similar. Of course, we can't take the same definition because we don't have one particle that is moving around. So we need kind of to find an equivalent of this transition probability. Yeah? So in particular, we would like to have a function S. Yeah? We would like to have a function S that satisfies this following initial condition that is really the Dirac at 0. Yeah? Assuming that your particle starts at 0. Yeah? So we would like to find a function that maybe has this property. What turns out, so this is simply something you need to believe, is there is something like this. Yeah? And then we were very much inspired by the literature, so otherwise I'm not sure if we would have come up with that one. Is that if you take half Laplacian, doesn't matter how you define it, you can do this, of your solution, then this function indeed satisfies this property. Yeah? So something that you need to believe. And so this motivates this definition. Yeah? So this 2 is here because, well, the factor in front of the Laplacian is 1/2, but it doesn't matter much, of course. Now, so this is our definition. So you see with the integral of space of x squared, expectation of minus Laplacian to the 1/2 h of tx times minus Laplacian to the 1/2 h of 0, 0. And here you need to think really about the smooth equation and integrate it in space. Yeah? So that's really a definition that we stole a little bit from particle literature about the one-dimensional KPZ equation. And so just to summarize what I just did is that if this guy goes to 0 as t goes to infinity, this implies subdiffusive behavior. If it's of order constant, it would mean you have diffusive behavior. And if it goes to infinity, this would imply super diffusive behavior. For the one-dimensional KPZ equation, we know that d bulk is of the order t to the 1/3. So it goes to infinity. So it has super diffusive behavior, which really means that the nonlinearity matters a lot. Yeah? Okay. And so having in mind now Wolff's conjecture, so what we thought is that in our case, the diffusion coefficient really should give constant order. This was kind of the conjecture that we had, following Wolff a little bit of what we understood from it. However, it turns out this is not the case. So it turns out that this debug, the diffusion coefficient, actually explodes logarithmically. Yeah, explodes logarithmically. So you see it's lower bounded by some constant times log t to the delta, and upper bounded by some other constant times log t to the 1 minus delta. Yeah, which really implies that the diffusion coefficient really will explode. So in particular, this implies that the KPZ equation is not diffusive. So to us, it came as a surprise. And what we think is that the value delta here is 1/2, and we may be able to prove it actually. And so in particular, what it suggests, if this would be true, is that the correct scaling of this equation is not this one, but the one where you divide time not only by x squared, but also by the square root of log. Yeah? This is what it really suggests. Yeah? So this really means that the scaling argument that I gave at the beginning is probably not completely the correct one, kind of it misses some logarithmic correction.
Yes, so does it mean that the scaling should be the same for the isotropic and anisotropic case? Because, okay, is the square root of log epsilon the same as the one we found out when q was equal to identity, or is it a different one?
It's, okay, morally equal, but if you now check what equation this guy satisfies, then you will have also something in front of Laplacian, right? Which was not the case here. Where is it? Here. So if you rescale time, I think then you get an additional factor in front of the Laplacian. It's not entirely the same, but it's in spirit is not the same. So this you see once you do the computations. Okay. But I mean, that's still a very good point. And so now you can ask yourself, why is this the case? I mean, why does this bulk diffusion coefficient explode? So for instance, for the linear equation, we can compute it in simply 1. So it's constant to 1 for all times. So this means that the source of this diffusion coefficient exploding must be the nonlinearity. It must be the nonlinearity. So then as the first step to try to understand what could happen in this scaling, we look at an equation that's slightly simpler, which is what we call the weak AKPZ, which is the same that was considered in the anisotropic regime. Yeah? It's not completely the same as the one when you do the computation where you take this rescaling. So we will look at this equation, kind of to kill a little bit the divergency of the nonlinearity. Yeah? And so what do we know in this case is that if you look at this equation, epsilon goes to 0. Yeah? So h epsilon is tight, so it has subsequential limits. And we also know, I mean, now what could happen is nice, it's tight, but it's tight because you simply kill the nonlinearity and essentially look at the linear equation. But this is not what's happening here. So what we showed is that as epsilon goes to 0, any subsequential limit will be different to the equation where you simply put lambda to 0. It does not mean that if you would be able to prove a scaling limit, that the scaling limit is not is the stochastic heat equation, but it's simply not the one where you simply put lambda to 0. Yeah? So it really means you do something sensible here. You don't completely kill the nonlinearity, but you take care of its divergency, but still leave some interesting part. Okay. One thing that is maybe, okay, it's the same scaling as for the isotropic case, but one thing that is interesting and which kind of points at that Wolf was not completely wrong is that in this case, this result holds for all lambda. Yeah? In the isotropic regime, the result I was writing down, it only was holding for lambda small. So there was a phase transition. We don't observe a phase transition here. So it really shows that these two equations with the plus and the minus, they're really different. The diffusion feature.
Okay. Yeah. You said that, okay, so you prove that any limit point is different, but do you know, okay, in the isotropic case, the limit was different,
yeah,
but it was just a difference in the intensity of the noise, right?
Exactly. It was.
Here, can you disprove that the difference is not this one, or? Yeah,
so actually this comes, I think, in 2 slides.
Okay.
Yeah, this comes in 2 slides. So let me first go to the first main result and then to the second one, which is exactly the one you were asking about. So now, I mean, you have this equation that, yeah, as Huber was essentially asking, now you would like to know, okay, you have subsequential limits, but you have a limit. And if so, what is the limit? Is the limit still a stochastic heat equation with different coefficient, or is it something completely different? Yeah. So the first thing you can do is you take this equation and you look at this diffusion coefficient. So now the question is, with this equation, is this equation now diffusive or still super diffusive, or maybe subdiffusive? Yeah? And it turns out the answer no, it's diffusive. Yeah. So if we compute the bulk diffusion coefficient at level epsilon, let epsilon go to 0, then for any time t, the bulk diffusion coefficient converges to an explicit constant, which is this nu f, the effective diffusion constant, and which we know is given by the square root of 1 plus 2 lambda squared divided by pi. Yeah? So it's explicit. It holds for all lambda. So again, you don't see any phase transition here. But the interesting thing is that this effective diffusion constant is larger than 1. It's strictly larger than 1 as soon as lambda is positive. Yeah? Why is this the point that is worthwhile to mention? It's worthwhile to mention because if in this equation above lambda would be 0, then the bulk diffusion coefficient would be simply equal to 1. So this means even though we get a diffusive behavior, it is not the one of the equation where lambda is equal to 0. The diffusion coefficient really changes by something non-trivial. Once you have this, I mean, at least you can write down a conjecture for what the limit should be. And well, you always hope that is maybe still a stochastic heat equation, because this object you kind of understand. If it would be something completely other, something really crazy, then okay, then you lost essentially. And well, this turns out to be the case. So what the recent work we showed is that for each fixed lambda, h epsilon, which is the solution to this equation here, h epsilon converges to a certain h lambda as epsilon goes to 0 in law, where h lambda solves this equation. Yeah? So it's dth lambda, the effective coefficient nu f divided by 2 times the Laplacian of h lambda plus square root of nu f times psi with the same coefficient as before, which is strictly larger than 1. Okay. So, I mean, first of all, it's nice. So now we really have a scaling limit, and to the best of our knowledge, the first one for a critical equation where there's no representation of the solution. The other thing that shows this equation is different from the one that we saw for the isotropic regime. In the isotropic regime, you only gained a constant in front of the noise, meaning that in the isotropic regime, the nonlinearity kind of converged to some independent noise. Yeah? In our case, it turns out that you gain something in front of the Laplacian and you gain something in front of the noise. So this means that the nonlinearity splits into a Laplacian and splits into a noise. Yeah? So that's maybe a bit different. maybe one comment to make here. So, I mean, you see here you have nu f divided by 2, you have square root of nu f. So actually, this is kind of expected. So once you know that part of the Laplace or part of the noise will be reproduced by the nonlinearity, then it must be kind of in this way. Maybe the constant, of course, you don't know, but it must be kind of in this way that the constants are related in the way they are, simply because we are looking at a stationary situation. And so in the limit, you want to have, so the inverse measure never changes, it doesn't depend on epsilon. So at the end, you want to have an equation which has your inverse measure as inverse measure. Yeah? And it turns out it must be of this form. There's no other way. Okay, so I think I'm running a little bit out of time, so maybe I will spare you the proof part and stop here maybe.
Okay, thank you very much, Dirk. So we have plenty of time for question. So in particular, if somebody wants to ask questions about the proof part or any other thing, yeah, maybe Leandro, you can unmute yourself.
Hey, Jake. So I suppose that when you're approaching a critical equation, you like if you somehow modify the Laplacian to be a slightly bigger part of the Laplacian and you cut it down to it bit, what you would have is that you would have more and more symbols if you're looking from a regularity structure, right?
Yes, exactly.
Can you characterize what happens to those symbols? Like, or does that make sense? Because as you're approaching criticality, you get more and more symbols. Do they all collapse to one? Is there any idea of what happens to this expansion? Does that make sense?
Yeah, it makes perfect sense. So first of all, yeah, so if you're at criticality, the number of symbols is infinity, right? So that's why actually, if you're at criticality, you shouldn't use regularity structure, so it doesn't seem very promising. I think but I mean, when we started this whole project, I think we computed the first and it should converge to white noise. So I guess if you combine all of them, they converge to some kind of a combination of the white noise or so.
Oh, okay. No, thanks. I was wondering.
Yeah, but I mean, I think we did it for the first symbol, but so I mean, you can write them down, right? But the computations become harder and harder. So we never did this for, I think, the higher order symbols, only for the first, for this one.
Sorry, my internet fell for a second. I just meant to thank you for.
That's okay.
Yeah.
Milton has a question.
Yeah. So do you have a quick explanation by the square root of 2 lambda squared divided by p plus 1?
No, I mean, the pi, of course, comes from computations in the Fourier space. But I don't have a simple explanation. Turns out result of the computation somehow. Yeah, sorry.
Well, and for this log epsilon scale, you have an explanation for that? Or?
Yeah, so what if you have a conjecture for that?
An explanation why this is the scale at which you observe.
Yeah. Right, okay. So this actually comes from a question that is very related to the one of Leandro. So if you, I mean, one way to try to solve the equation is to do some kind of a naive Picard iteration. Yeah. So maybe your first guess of the iteration would be the linear equation. Then you plug it into your Picard iteration, and then you see what it produces the next term. And this is one of the terms Leandro was talking about. And then you can study this term, and then actually what you observe is that this term diverges. But if you divide it by the square root of log epsilon, or epsilon to the -1, then it exactly cures the divergency of this term. that's kind of a quick way of seeing it, that this must be the correct thing to look at.
Okay, thanks.
Welcome.
Yes, I had a question. In your last equation, somehow, if you take this new efficient in your, if you take it into your time scaling, can you get well, what happened? Does it? I guess okay. You can get you can take it out in front of the Laplacian if you change the time scaling, right? Then what happened to the noise term? Does it simplify it, or do you get it squared, or?
Oh, there's a computation I need to do. This has something to do with Brownian scaling.
Yes, no, it should be easy, but
yeah. So I can take one over mu, or it's no, it should be simply one. No, I think it should be simply one in that case. Yeah, I think it's simply one that you get. So
this thing is so it's the equivalent of an extra scaling in time, or
exactly. Yeah, I will need to do the computation, but I'm pretty sure actually about that. Yeah.
Okay. And do you have an idea of why was what was the argument for this anisotropic irrelevance claim, and what is wrong with this heuristic, or is it really wrong? I don't know.
No, so yeah, this is not so clear for me. So we never, I mean, it's a physicist paper, so we never really completely understood what he's exactly claiming. So it's hard to understand it for a mathematician. I mean, he uses some kind of renormalization group arguments, which I would definitely not be able to reproduce. But my understanding is that maybe we mathematicians okay, so since it was never really clearly stated, it's hard to say this, but maybe we really understood it wrong, and that really the equation to look at is the one where you rescale, where you have some additional rescaling in time, and this should now have the same behavior as the stochastic heat equation. So this is my current conjecture that this is what he meant.
Okay, so the morality of the story is that if you make claims that are difficult to understand, you have more chances to be right.
I think in the math community, my feeling was that, at least the people I talked to, is that you do, I mean, that taking the usual diffusive scaling, then you should see something Gaussian, but this doesn't seem to be the case. So maybe he meant it with this additional log factor. That's my guess.
Okay, thanks.
Okay.
I don't see any more hands, but has anybody any more questions for Dirk? No. So I guess we can all thank Dirk for this very nice talk.
Thanks a lot.
And there is a congress next week with a probability session, so there will be no seminar. And there will be a seminar 2 weeks from now, so on the day 22.
Okay. So
bye.
Bye. Thanks a lot.